So this describes the state of a system independent of a process or a path, okay? You can just look at a system in the state it's in and answer the question about, say, temperature, okay? And it doesn't really matter what temperature it was before, what temperature it's going to. Temperature it was before and temperature it's going to might be related to the flow of heat. But the temperature itself is a single measurement that I can take, okay? And it is a measure of average kinetic energy of the particles of a substance or of our system, like not be just one single neat substance. Okay, we're going to always use temperature in Kelvin, but I guess sometimes to be mean, we'll give it to you in Celsius and make you convert it first. I don't know. But this will be given to you. You don't have to memorize it, although I'm sure many of you have. But Kelvin is degrees Celsius plus 273. Okay. So what's absolute zero in Kelvin?
Zero.
Okay, absolute zero is 0 Kelvin by definition. It is the absence of temperature and thus the absence of particle movement. Okay, if temperature is a measure of kinetic motion or movement of particles, then if you have no temperature, you have no movement. It's where everything slows to a complete stop. And that sort of forms the basis. It's an important piece of the third law, but then also thermal equilibrium and temperature as a measurement of thermal equilibrium is the zeroth law. Okay, so two systems. I have 2 more slides that go through this. I don't know why I doubled it up, so don't panic. You don't get to like write this sentence down. But 2 systems that are considered to be in thermal equilibrium are at the same temperature. Oh, I made a note to myself. We will define the equation that relates kinetic energy and temperature next time. So for now, we'll define all the terms, and then next time we'll use them. Okay, so the zeroth law is, again, if 2 systems are in thermal equilibrium with a third system, then you could say those 2 systems are also in thermal equilibrium with each other based on a measurement of temperature. So here we have, I don't know what I was thinking, with a hand holding an ice cube or a hot cup. Hot item, the heat will flow into the cold item. So here, the ice doesn't actually feel cold. Heat is just leaving your hand to go into the ice cube. There's a whole, I have a presentation where I talk about a heat pack and an ice pack, and I will present it in part of chapter 9, I believe, so for exam 3. And there are definitely some students who are like, I don't really understand how this ice pack works. I'm like, we just went through it. So you guys you'll nail it. Okay, so heat will flow from hot to cold until we come into thermal equilibrium. And again, you could use temperature as your indicator at 2 and 3. If they're in equilibrium with each other, if they are both at the same temperature. And here's just, again, for the 3rd time. Heat stops flowing. The temperature A is equal to B and B is equal to C. A is equal to C. I guess this is an important point for a question at the end. This will continue, heat flows continually until thermal equilibrium is reached, at which point they'll both be at the same temperature. I don't know why it's in quotes. That's weird. Any questions about this? And do you think the zeroth law came first? It came 4th. It came last. They defined this after they made 1, 2, and 3. Okay, another state variable. Remember, a state variable is independent of a process or path. At an instant, I can take this measurement. Pressure is another example, which is most simply defined, as we've seen it before, force over area. Okay, so let's first define the force piece. Force is mass times acceleration. Okay, and that's going to be given in kilogram meters per second, which is also equal to 1 Newton. I don't have this memorized, so I looked it up before class. What does like a Newton feel like? What's an object that weighs like 1 Newton? Beautiful, okay. Apple is the one, and then I guess that's supposed to be sort of poetic with Newton, I don't know. If you believe that the apple really fell on his head and that's how he discovered gravity or whatever. But I never know these. The next one is even harder. I tried to look up how to feel a pascal of pressure. That one they said to put a die, like a 6-sided die in your hand, and then put a 1 kilogram weight on top of it. And that amount of weight over that area would feel like 1 pascal. So I don't know, maybe we could try that sometime. But it's often hard to imagine what these really are like, okay? So if pressure is force over area in newtons meter squared. Newtons meter squared is our 1 pascal. Okay. Here are a whole bunch of conversions for pressure units. We have newtons meter squared to pascals, we have dying centimeter squares, we have bar, we have atmospheres, we have torr. You don't have to memorize them, you would be given them. You may be asked to convert from one to the other before you go forward with your equation. Okay? So just be prepared to read your question carefully and see what units it's giving you so that you get into the right units before you move on. And again, like I said, you don't have to memorize any of that. This is a nice table in your textbook. I think it's 620 something, 624, one of the pages in there. So this has a nice key units for many of the things that matter, and basically also standard units. We're going to be in meters, we're going to be in kilograms, meters cubed.